Cool. All right, so if we're gonna do this using vertical, I should say to the people watching the video, do this problem, give it a shot. For setting a double integral using vertical cross sections, we're thinking, well, really, we should think about what all these boundaries are. So this line here is going through the point 0, 1 and -1, 0. We can also find the slope and the right, but this is definitely the line y equal to x plus 1. Up here, we have the horizontal line y equal to 5. And over here, on the left-hand side, we have the line x equal to -3. So if we're going vertical, our inner integral is going to have a lower bound of y equal to x plus 1 and an upper bound of y equal to 5. So our inner is going to look like y equal to x plus 1, y equal to 5, dy. And you can put the y equals if you want to. I really do like to write the y equals. I find it helpful a lot. And then the outer integral is going to be x going from -3 all as far right as x equal to 4 dx. And you don't have to, but I like to put a 1 in there. Not required, but I think it makes it, I just reminds me what I'm doing. Or if we want to go horizontal cross sections, or our left-hand function is x equal to -3, and our right-hand function, if we solve for x, we're going to get x equal to y minus 1. So doing it that way, our inner integral will be a left-hand boundary of x equals -3 to a right-hand boundary of x equal to y minus 1 dx, and then a lower y value of -2 and an upper y value of +5. Again. Yeah. Now I should point out, just because we're pointing out, if someone actually asked you to calculate this integral, you could do it this way, but it seems kind of silly because it's a triangle. So if you're just trying to find the area of a triangle, you can just say, well, the base is from -3 to 4, which is 7. The height is from -2 to 5, which is also 7. So the area is going to equal 1/2 the base times the height, which is going to be 49/2 or 24.5. Which should come out to be what it is if you actually did the double integral. But when you are, so usually someone would, a more typical question would be to like ask you to integrate some function over this region. There's one other double integral problem I saw that I want to kind of address before we start talking about sequences, which is the one I saw this one in the homework, and it made me think of a couple things. So let's say we've got the integral from 0 to 6 of the integral from 2 to 5 of the square root of x plus 4y dx dy. So looking at this, you can do a u substitution. You don't actually have to do u sub, although I think we should just kind of talk about how it works. So inside here, inside the square root, I see x plus a constant. So for this inner integral, or for the integral of the square root of x plus 4y dx, I'm going to let u equal the inside stuff, x plus the constant. And my du, well, in fact, let's write it more derivative like. My du dx is just 1 plus 0, if you like. Or du is equal to dx. So this really becomes the integral of the square root of u du, which is the integral of u to the 1/2, which is just going to be u to the 3/2 times 2/3. And then if we plug back in what u is equal to 2, it's 2/3 times u, which is x plus 4y to the 3/2. And that's probably how I would choose to approach it. You could change the limits of integration, but I didn't really want to, because so I would point it, if you change limits of integration, your lower limit of integration when x is 2, u is going to be 2 plus 4y, and your upper limit when x is 5 is going to be 5 plus 4y. It just kind of feels weird to change from constants to not, although it's totally valid. But I would do it this way and then say, okay, my inner integral, well, we just said the integral of square root of x plus 4y is 2/3 x plus 4y to the 3/2. I'm going to get 2/3 x plus 4y to the 3/2 from x equals 2 to x equals 5. I would pull out the 2/3 as a constant. And now we're just going to plug in the 5 for the x and the 2 for the x. So we're going to get 5 plus 4y to the 3/2 minus 2 plus 4y to the 3/2. But you can't put together in any meaningful way. So then I would say you can kind of do another use of if you wanted to. So here's what I would point out. Let's see, I've got nothing. So going up here for a second, if we're integrating a constant plus 4y to the 3/2, doesn't matter if it's 5 or 2, the pattern's going to work out the same. If you let u equal that constant plus 4y, then your du is going to be 4 dy, or 1/4 du is going to equal dy. So this is going to become the integral of, well, it's going to be 1/4 u to the 3/2 du. And then that'll be 1/4 times 2/5 u to the 5/2. And then you can plug back in your u, whether it's c plus 4y or 5 plus 4y or 2 plus 4y. So each of these integrals is going to be 1/4 times 2/5 times your stuff to the 5/2 power. So I'm going to get, let's see, so I'm going to get, I could probably, let's factor out the 1/4 as well. Let's be smart about this, because they're both going to get a 1/4. But I'm going to get a 2/5 times 5 plus 4y to the 5/2 minus 2/5 times 2 plus 4y to the 5/2 from 0 to 6. I would again factor out the 2/5 as well. So I've got a 1/4 times 2/3 times 2/5. I could probably simplify that. I can, right? The 4 and the 2's cancel. That's really just 1/15. And then in here, I've got a, so I'm going to plug in the 6 first. I'm going to get a 5 plus 4 times 6 to the 5/2 minus 2 plus 4 times 6 to the 5/2 minus, let me plug in 0 and we get 5 to the 5/2 minus 2 to the 5/2. It's kind of gross. If we simplify this one more step, we're going to get a 1/15 times, let's see, 5 plus 24 is 29 to the 5/2 minus 2 plus 24 is 26 to the 5/2 minus 5 to the 5/2 plus 2 to the 5/2. So it's kind of the stupidest answer I may have ever seen, but it's fine. None of these simplify nicely, right? None of those are nice square numbers. It's just going to come out weird. Just going to come out weird. Yeah, but the point I wanted to make here was really just seeing the u substitution, that you can let u equal x plus 4y, and then your du is just 1 dx. Or if you're doing it with respect to y, your du is 4 dy. So yeah, it's okay to pick a u with both variables in it. All right, let's change gears a bit. Let's talk about sequences. So sequences and eventually series. Series, or a better word is sums. But people say series, so yeah. So sequence, what do I want to say about sequence? A sequence is really just a list of numbers in a specific order. Or you could say it's a set of numbers in a specific order. So let's look at some examples here. Yeah, so let's look at this first one here. Typically, we describe sequences as some a sub n equal to something like 6n plus 1 over 2n plus 5, where the nth term of the sequence a sub n depends on the integer n. And typically, although, so I should say, usually if it's not stated, we assume that n starts at 1, although your teacher might have said 0. So typically n starts at 0 or 1. I like to start at 1 because it's easiest to then use the language of starting at the first term of the sequence. So I could say a sub 1, if I just plug in 1 for n, it's going to be 7 plus 1, sorry, 6 plus 1, which is 7, over 2 plus 5, which is also 7, which is 1. And then my second term, I'm just going to plug in 2, and we get 6 times 2 plus 1 over 2 times 2 plus 5, which is going to be 13 over 9. And so on and so on, right? So, I mean, I should say it starts to feel a little monotonous when you do this for a while, but we can keep going, right? The third term is going to be 6 times 3 plus 1 over 2 times 3 plus 5. And that's going to be 18 plus 1, which is 19, over 6 plus 5, which is 11. And the fourth term would be 6 times 4, which is 24, plus 1, which is 25. And 2 times 4 was 8 plus 5, which is 13. And it goes on this way. A typical question we like to ask is, does this sequence converge or diverge? Which specifically means, so we can rephrase this as, does the limit as n goes to infinity of your sequence exist or not? So if the limit exists, we say the sequence converges to that limiting value. And if the limit doesn't exist, we say the sequence diverges. We might be slightly more specific, we'll talk about it in a second. But for this example, we're just going to take the limit as n goes to infinity of 6n plus 1 over 2n plus 5. And you can kind of apply whatever methodology you might have learned before, but we're going to see a lot of rational functions where you have powers of n over powers of n. We could do it the long way and say, I'm going to divide everything by the highest power of n and get the limit as n goes to infinity of 6n divided by n plus 1 divided by n over 2n divided by n plus 5 divided by n, and then the parts that are being divided by n go to 0. And we're left with 6 over 2, which is 3. Or we could have used the shortcut where, since the degrees are the same, we can just use the quotient of leading coefficients, which is totally fine to use, but it's good to remember this as well. So we would say the sequence a sub n equal to 6n plus 1 over 2n plus 5 converges to 3. It could actually equal 3 at some point. It doesn't. But what we mean when we're just saying, just like a limit, this sequence is just getting closer and closer and closer to the value of 3 as n gets larger and larger and larger. Most of the time, they won't ever actually equal what they converge to, although sometimes it's possible depending on what kind of weird sequence you have. Questions so far? Okay. Yeah, let's look at another example. Yeah. Let's say we have a sub n. So a sub n is kind of the standard choice, but you really can use any letter. You can say b sub n or c sub n or d, right? Any like whatever sub n is typically how we write them. Let's say that a sub n is equal to 6n squared plus 3 over 2n plus 5. So again, I don't find a lot of use in writing out terms. Typically, I mean, it's good to write out terms to kind of see how things work. But if we start writing out terms, right, our a sub 1 is going to be 9 over 7. A sub 2 is going to be 6 times 4, 24 plus 3 is 27 over 4 plus 5, which is 9. I will say, as we do more of this, it's usually not in your interest to simplify terms. Meaning, I know 27 over 9 is 3. But often what we're going to be doing is working kind of backwards and be starting with some first 5 terms of the sequence and trying to figure out what the formula for the sequence is. And it's usually much easier if those terms are unsimplified to kind of identify what patterns are happening. But if we keep going on here, third term is, let's see, 6 times 9. I mean, it's just doing some arithmetic. take 6 times 9 is 54 plus 8 is 57 over 2 times 3 is 6 plus 5 is 11. And fine, we'll do one more. 4 squared is 16 times 6 is 96 plus 3 is 99 over 8 plus 5 is 13. And it goes on. And it looks like my terms are getting bigger. I mean, well, they were in the last one too, I think, right? This first one was 1, and then bigger than 1, and then bigger than 1, and then bigger than, right? So they were getting bigger. These ones also seem like they're getting bigger, right? A little more than 1, 3, more than 5, more than, I don't know, 7 or 8, 7. So does this one converge? Or diverge? Well, if we take the limit as n goes to infinity of 6n squared plus 3 over 2n plus 5, we can see that the power on top is a higher degree than the power on the bottom. So we know that this is going to get infinitely large. And you could show the same work. You could say, well, it's going to be the limit as n goes to infinity. Divide everything by the highest power by n in the denominator. So we divide by n and we get 6n plus 3 over n over 2 plus 5 over n. And then these go to 0. But we're left with infinity over 2. Or infinity. So even though this limit is infinity, we say that this diverges because the limit doesn't exist, right? Infinity is not a real number. The limit to infinity doesn't exist. We're just being more informative when we say the limit to infinity. So we're saying the limit doesn't exist and the function gets larger and larger and larger. I will point out, typically when when something diverges in this way, I would say that a sub n equal to 6n squared plus 3 over 2n plus 5 diverges, and I would probably include the words to infinity. It's usually information we like to include if it's true. On the other hand, just to kind of point out another example, if my sequence was instead, yeah, sure, I've got enough room. If my sequence was b sub n equal to -1 to the n times the previous sequence, 6n squared plus 3 over 2n plus 5, that -1 to the n is going to make the terms alternate signs. So we can see that b sub 1 would be -9/7, and b sub 2 would be +27/9, and b sub 3 would be -57/11, and b sub 4 would be +99/13, and so on and so on. And then if we took the limit as n goes to infinity of b sub n, which is the limit as n goes to infinity of -1 to the n times 6n squared plus 3 over 2n plus 5. Well, the problem is we're getting really, really large, except we're getting really positively large on one term and really negatively large on the next term. So we're bouncing further away from, like, we're kind of doing something that looks kind of like this. We're kind of doing something graphically where, you know, my first term is -9/7. And my next term is +27/9. My next term is a bigger negative number, and then a bigger positive number, and then a bigger, right? We just keep bouncing further and further away from getting close to a particular number, but we're also not growing necessarily always positively infinitely large or always negatively infinitely large. So here, this limit just does not exist. We can't really say anything else meaningful about it. And we say that the sequence b sub n equal to -1 to the n times 6n squared plus 3 over 2n plus 5. All we can say is that it diverges. We can't say anything else about it, like diverging to infinity or negative infinity. We just say it diverges. Let's look at one more example, one more alternating example. Let's say we had, well, we'll probably do a few more examples. Let's say we have a sub n equal to, what do we got here? Sure, let's do that. To -1 to the n plus 1 times 6n plus 7, 6n squared plus 7 over 3n squared plus 1. So again, when we see this -1 to the n or n+1, although really you can have -1 to kind of any power, those are usually the two choices you'll see. One of them, if you want to start with a negative number, one of them, if you want to start with a positive number. And again, we're usually making the assumption here that n is starting at 1, unless someone has said otherwise. So someone might write this and be like, and then say something like, and let's start at 0. So n is greater than or equal to 0. Again, the assumption here that we're all making is that n is only going to be positive integers. A sequence is like a function where the domain is just the positive integers instead of the domain being any possible real number. That's kind of the difference between a sequence and a function. But it is a function. So here we could write terms. I don't really want to. A sub 1. My first term is -1 to the 1 plus 1. So positive 6 plus 7 over 3 plus 1. Oh, it says I said it's supposed to start at 0. That is my a sub 1 term. 3 plus 4. But my a sub 0 term should have been -1 to the 0 plus 1. So negative, and then 0 plus 7 over 0 plus 1. And then my a sub 2 term is going to be, well, -1 cubed. So negative, and 6 times 4 plus 7 is, sure, I can do math, 31 over 3 times 4 plus 1 is 13. And it goes on. We've got this alternating thing. Now, we can see that if we look at the limit, if I'm looking at the limit of this kind of thing, I usually like to look at the limit of the non-alternating part first. So if I want to see about convergence or divergence, I'm going to look at the limit as n goes to infinity of just the non-alternating part first. And I think you would agree that this limit is going to be what? Right. Which means that our alternating sequence is bouncing back and forth between numbers that are getting close to 2 and numbers that are getting close to -2. But unfortunately, that means that the limit doesn't exist, because what's going on is something that looks kind of like the previous picture, except we're starting off at we start off at -7. So way down here at -7, and then we bounce up to 13/4, which is a little more than 3. And then we bounce down to -31/13, which is still a little bit more than 3. And we're just going to keep bouncing back and forth like this, getting closer and closer to 2 and -2. But the problem is we're not getting close to any one value. And for a limit to exist, we have to be getting close to one and only one value. So this limit also does not exist. So fun fact, an alternating sequence converges if and only if it converges to 0. Write that down. So an alternating series A sub n converges if and only if it converges to 0. For example, the alternating series sequence A sub n equal to -1 to the n plus 1 times n plus 3 over n squared plus 4. That sequence will definitely converge to 0, because even though you'll have terms that are positive, but terms are negative, they're both going to be getting close to the one term that both positive numbers and negative numbers can both get close to simultaneously, which is 0. So this definitely converges to 0, because the limit then goes to infinity of n plus 3 over n squared plus 4 is 0. So we can also say the limit as n goes to infinity of -1 to the n times n plus 3 over n squared plus 4 is equal to 0. It's kind of neat. So typically, not really true. I was going to say we don't really do a lot with sequences. We do more with series, but technically everything is in terms of sequences, because really what we're going to do is we're going to think about a series being a sequence, just in a different kind of context. But the other thing we like to do with specifically just sequences that haven't been like all added up together and then thought of it anyway, is we like to kind of try to work backwards from the given first so many terms to see if we can figure out what the sequence it came from was. So for example, someone might give you these first few terms. Let's say we have 2/3, -7/5, +12/7, -17/9. And I will say there's a few things to look for when you're looking to see what the pattern for a sequence would be. Or as you might phrase this, we want to find an expression for the nth term of the sequence. So if I was writing this down, I would say, okay, I know this is my a⁻1, this is my a⁻2, this is my a⁻n, this is my, a⁻3, my a⁻4. It might, if you're thinking about this, pay to kind of just make a guess and see, can I even guess what the next one's going to be? So if I want to figure out a guess for a⁻5, what do you think the denominator is going to be? Right. What do you think the numerator is going to be? Right. Now, it would be kind of terrible. So let's say I had given you this problem and given you the first 5 terms. If I had written that as 2, it makes it a little bit harder to see what the pattern is. Probably not impossible, but harder. So one thing to look for when you're looking to see what the pattern for sequence is first, things to look for. There's a few things. Thing one, I guess the first thing you can look for is it alternating, right? That's always an easy thing to see. This one definitely is. So we're going to get a -1 to the n or a -1 to the n plus 1. Another thing to look for is, or another thing to really kind of do is to consider the numerator and the denominator separately. Usually they are kind of not really related to each other. And then there's kind of 3 patterns to look for after that. So one pattern to look for is the difference between the terms is always the same. So constant difference. Like we see in this pattern, right? You see in the denominator, the difference is always 2. 3 + 2 is 5, 5 + 2 is 7, 7 + 2 is 9, 9 + 2 is 11. So whatever that constant difference is, you're going to have that number times n. So I know that for this sequence here, my a⁻n, I'm going to have a 2n plus or minus something on the bottom. And I'm going to have a 5n plus or minus something on the top because both of those are constant differences. I'm ignoring the negative signs so I know how to deal with the alternating part. And actually for this one, that's all we really need to do. So here, now we have to figure out what the difference is. So if a⁻1 is 3, and I have a 2n in the bottom, well, that's 2 times 1. I need to add 1. So that I get a 3 in the bottom when I plug in n equal to 1. Right? My a⁻1 has a 3 in the bottom. a⁻1, I need 2 times 1 plus 1. And I double check with the next one, right? If I do a⁻2, 2 times 2 plus 1 is going to give me a 5 in the bottom. Great. For a⁻n, and again, I should really be just thinking this is 2/3, +7/5, +12/7, +17/9, and we'll deal with the negative alternating part at the end. If I plug in n equals 1, 5 times 1 is 5, but I want to get 2. So what do I need to do? Right. And then we need a -1 to the, do I want an n or an n plus 1? Right. You could also do n minus 1. That just achieves the same result. People sometimes prefer that. I don't really know why. And there's the formula for the nth term of our sequence. There's 2 other things that I'm going to come back in and fill in here because we haven't seen them yet. So let's actually look at a couple other examples and then we'll come back to this. So there's a few other things that come up like, yeah, let's look at these 2 things actually. So let's say we're just going to write out some terms. We're going to go back to the previous topic and just talk about things that look like this. Yeah, it's kind of funky. n cubed over 2 to the n. So if I start writing out terms, a sub 1 is 1 over 2. A sub 2 is 8 over 4. A sub 3 is 3 cubed, which is 27 over 2 cubed, which is 8. So it's looking like terms are getting bigger, but hold your hat, hold on to your hat. A sub 4 is going to be 4 cubed over 2 to the 4th, which is 64 over 16. Okay, still bigger, but now a sub 5 is going to be 5 cubed over 2 to the 5th, which is 125 over 32. Still bigger. So I have to go. So I should have picked a bigger denominator as the problem. This will eventually start getting smaller. So we look at a sub 6. That's going to be 6 to the 3rd over 2 to the 6th, which is 6 to the 3rd is 216. 2 to the 6th is 64. And that actually is smaller, right? 125 over 32 is a little bit smaller than 4. 216 over 64 is definitely way smaller than 4. And if we go a couple more terms, a sub 7 is not super helpful. 7 cubed over 2 to the 7th is 343 over 2 to the 7th is 128. That's less than 3. And we'll do one more just to kind of show. A sub 8 is going to be 8 to the 3rd over 2 to the 8th. 8 to the 3rd is 2 to the 3rd to the 3rd, which is 2 to the 9th. And 2 to the 9th divided by 2 to the 8th is just 2. So things are going to get smaller eventually. So the one thing I want to point out here is that another pattern to look for when you're trying to kind of reconstitute the formula is if you have something that's multiplying by the same amount every time. So in this denominator, here the denominator is doubling every time. So to go back to my previous page for a second, constant difference or constant multiplier, like doubling or tripling. So like for a constant difference, you're going to get n times that difference. Whereas for a constant multiplier, you're going to get that multiplier raised to the nth power. Like in the previous one, right? We multiply by 2 every time and we end up with a 2 to the n. Does this converge or diverge? Well, from what I said, we might think it's going to converge because I said the denominator eventually gets bigger, and it does. So, but how do we show that this limit as n goes to infinity of n cubed over 2 to the n, how do we show that that limit exists? Because what we have right now is infinity over infinity. And I don't know how much your teacher is really going to ask you about this particular kind of thing, because he might not at all. There's 2 ways to show this limit is what it is. One way is just to write words and say 2 to the n is an exponential function, and 2 to the n definitely outpaces or outgrows any polynomial. My coworker Grant likes to write this infinity over infinity as infinity over infinity. So the bottom infinity is much, much bigger than the top infinity. It doesn't look like it yet because the terms we wrote out here, but eventually, like if you're plugging in like 2 to the 10th is 1024 and 10 to the 3rd is 1000. And so at that point you actually are getting the denominator bigger. 2 to the 20th is huge. 20 cubed is not. So right, the denominator is definitely outgrowing the numerator. But the actual way you would show this if you were trying to show all of your work is you'd use L'Hopital's rule. So if I use L'Hopital's rule, because I have an infinity over infinity type, the derivative of the top is 3n squared, and the derivative of 2 to the n is 2 to the n times the natural log of 2. It's still an infinity over infinity, so we do it again. The limit as n goes to infinity of 6n over 2 to the n times natural log of 2 times another natural log of 2. Still infinity over infinity. So we do it one more time. And we get the limit as n goes to infinity of the derivative of 6n is just 6. And the derivative of 2 to the n one more time is going to multiply by another natural log of 2. So we have a natural log of 2 to the third power. And then you have 6 over something that's going to infinity. So that's going to go to 0. Kind of annoying, but totally fine. The other type, oh, go ahead. Oh, sorry. So the other thing I want to mention, which you may or may not have seen before, is n factorial. Have you seen that? Yeah, factorials. So factorial is pretty straightforward. It just means you multiply by every lesser integer down to 1. So for example, 6 factorial is just 6 times 5 times 4 times 3 times 2 times 1. Something that comes up frequently is the 1 factorial divided by another factorial. So for example, if I had, say, 4 factorial divided by 6 factorial, I can't just cancel the factorials and get 4 divided by 6. What I can do is write them out and say, well, that's 4 times 3 times 2 times 1. That's 6 times 5 times 4 times 3 times 2 times 1. And then, oh, the 4s, the 3s, the 2s, and the 1s cancel. And you get 1 over 6 times 5, which is 1 over 30. A somewhat faster way to do this would be to write it as 4 factorial over 6 times 5 times, I know the rest after that is also 4 factorial. And then those 4 factorials can cancel because they're just the same thing. The reason I bring this up is because sometimes we're going to see something. Well, in fact, let's look at this next example. Yeah, sure. Let's say we had a sequence that was n plus 2 factorial over 3n squared times n factorial. And I want to write out some terms. So my first term is 3 factorial over 3 times 1 squared times 1 factorial. 1 factorial is 1. 0 factorial is also defined to be equal to 1. So that's actually kind of an important thing to note. 0 factorial is defined to be equal to 1. Kind of the same way that like 3 to the 0th is equal to 1, because we need it to be. So all the other rules of math that we like to work. That's also why 0 factorial has to equal 1. So all the other rules of math that we want to work actually work. Yeah, we can talk about it more later if we want. So here, if we do this, 3 factorial is 6. 6 divided by 3 is 2. And then a sub 2 is going to be 4 factorial over 3 times 2 squared times 2 factorial. So it's nice to kind of know what things are. So I should point out 0 factorial is 1, 1 factorial is 1, 2 factorial is 2 times 1, 3 factorial is 3 times 2 times 1. 4 factorial is 4 times the previous thing, which is 4 times 3 factorial, which is just 24. It's very kind of a recursive thing, right? You can find each next factorial by just doing the next number times the previous factorial. So 5 factorial is 5 times 4 factorial, which is 5 times 24, which is 120, and so on. The reason I mention this is because if you see the pattern 1, 2, 6, 24, maybe 120, you should be thinking, oh, that's looking kind of like a factorial. So I should be thinking about maybe that being somewhere in the pattern. And so on. Does this thing converge or diverge? Well, if we take the limit as n goes to infinity of n plus 2 factorial over 3n squared times n factorial, we definitely have an infinity over infinity type, and we definitely can't use L'Hopital's rule because you can't take the derivative of something factorial. There's no good way of doing it. So typically what you have to do here is either logic it out or first better, try simplifying the expression. So I see that I have n plus 2 factorial, which is really n plus 2 times n plus 1 times n minus 1 times all the way down to 3 times 2 times 1. On the bottom, I have 3 times n squared times n factorial, which is n times n minus 1 times all the way down to 3 times 2 times 1. Or as you might see, on top I have n plus 2 times n plus 1 times n factorial. In the bottom I have 3 times n squared times n factorial, and those cancel. So what I'm really left with here is the limit as n goes to infinity of n plus 2 times n plus 1 over 3n squared. If I multiply at the top, not that you really need to, but if I multiply at the top, I get n squared plus 3n plus 2 over 3n squared. And since I have the same degree on top and the bottom, that limit's going to be equal 1/3. So this sequence converges to 1/3. Usually if you find the limit, you don't actually have to write out the words that the sequence converges to 1/3, but it's good to know that when the limit exists, the sequence converges to that. So back to kind of starting with terms and trying to determine what the nth term formula is. Let's say we had the following. Let's say our first terms were 1/4, 2/9, 6/16, 24/25. I'll even give you one more. 120/36. Again, clearly the person writing this knew not to reduce their fractions, even though we could have reduced some fractions and made it harder. Let me ask you first, Reed, what do you see on top? Right. So here we have to kind of decide. Do we want this to be our first term or our 0th term? Let's say our first term. That's a sub 1, a sub 2, a sub 3, a sub 4, a sub 5. So on top, I see 1 factorial, 2 factorial, 3 factorial, 4 factorial, 5 factorial. So it looks like my top part is just going to be, I guess not right. It's just going to be n factorial. Because whatever n is, I'm just getting that number factorial. And what about the bottom? What kind of numbers do you see? Right, I see perfect squares. I see 2 squared and 3 squared and 4 squared and 5 squared and 6 squared. Well, remind you, the 2 squared is when we have, that's our first term. So that's when n equals 1, n equals 2, n equals 3, n equals 4, n equals 5. So if we're trying to find just when n equals n, what's the formula for that going to be? Right. So usually the thing I'm looking for when I'm trying to identify the pattern is trying to find some piece of it that's increasing by 1 every time. And then after I know it's increasing by 1 every time, I can write that in terms of n, because n is increasing by 1 every time. So here, our formula for this would be a sub n equal to n factorial on top over n plus 1 quantity squared. And again, that's starting at 1. Let's see, we're probably out of time. I feel like there's one other thing. Oh, no, that's fine. Yeah, we'll stop there.